We'll give it a shot, see what happens.
Now, apparently on the third week is when the attendance drops off. Because last week it was good. So I think I will wait a few minutes before I send around the attendance sheet. So today, we're going to start talking about chemistry, what I would consider chemistry, okay? The matter and the volume and all that stuff is technically chemistry, but that's not what you think of when you think of chemistry, right? And last week was all math, so you think that's math, you take math class, you don't come to chemistry to take math. So today, we're going to start talking about atoms, periodic table, something called ions, and to me that's chemistry. So atoms, we talked about, are the smallest piece of an element you can have and have it still be that element, okay? But atoms actually can be broken up further. There's something called subatomic particles. Outside of the nucleus, there are electrons. Electrons have a -1 charge. Every electron flying around has a -1 charge. In the nucleus, which is the very center of the atom, there are protons. Protons have a +1 charge. And then there are also neutrons, which have no charge. Okay? Neutrons aren't going to be all that important in this class. Protons will be somewhat important. Electrons define everything. Okay? When we talk about chemical reactions, especially in this class, the electrons do everything. Okay? Stuff in the nucleus doesn't do anything until you get into nuclear physics. We're not in nuclear physics. So protons and neutrons are not going to do anything for us. You just need to know that protons have a +1 charge, neutrons have no charge. Okay? Look at the mass of an electron. That's very, 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 very small, right? Look at the mass of a proton and a neutron. That's very, 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 very small also. Well, what do you notice between the difference in a proton and neutron versus an electron?
The electron has 4 more, what's that?
That number,
Yeah.
right? So, if these are -24 and that one's -28, what does that tell you about the relative size? Which one is smaller? The electron is smaller. It's so much smaller that we actually say electrons have virtually no mass. Okay? When we talk about the mass of an atom, we're talking about the mass of the protons and the neutrons. Okay? Imagine if somebody comes along and gives you that giant backpack, okay? And it's full of chemistry books. It's really, really, really heavy. And then someone gives you an expo marker to carry. It doesn't make a difference, right? This is nothing compared to that. That's basically what's going on here. The protons and the neutrons are so much heavier than the electrons, we can just ignore the weight of an electron. So we said that the protons and neutrons are in the nucleus, okay? And then electrons are in this, what we call electron cloud. Okay, we're definitely going to come back to the electron cloud. But when you picture an atom in your head, what I want you to picture is this solid ball, basically, in the center of the atom, made up of protons and neutrons, and then there's electrons just flying around outside of that. An atom, in its entirety, including the nucleus and the electron cloud, is about 10 to the -10th meters. Okay? The nucleus is about 10 to the -14th meters. What do you notice about those two numbers? These two numbers are very far apart, right? So does the nucleus make up most of the diameter of the atom, or very little of it?
Little.
Very little. So the nucleus makes up basically all of the mass, but basically none of the diameter. Which means that the rest of it is what? Electron cloud, which is mostly empty space. So an atom is mostly empty space. So a nucleus accounts for 99.9% of the mass, but very, very, very little of the actual volume or size of it. A penny has about 10 to the 23rd atoms, but at the atomic scale, a penny is almost all empty space. Why?
The electron clouds.
The electron clouds. So if you have these spherical atoms and you pack them as close as possible, basically what you end up with, say you have 4 nuclei like that, and the atoms look like that. Those 4 atoms take up that much space, but only that much actual substance, right? All of this other stuff is empty space. We can't see it. Well, we look at a penny and it looks solid to us. But really what it is these little suspended nuclei surrounded by clouds. The atomic number up here is the number of protons. No question about it, okay? So, how many protons does a cobalt atom have? 27. If I have an atom, and I was telling you, I have an atom that has 54 protons. What element is it? 54. All you have to do is find number 54, and whatever element that is, that's the element, okay? We name things based on the number of protons. The number of protons defines what element it is, okay? Everything else can change. Neutrons can change, like we'll see, and electrons can change. That doesn't change the element, because the protons never change. If you change the number of protons, you change elements. So if I have a molybdenum atom and I somehow remove a proton, it is now, wow, I don't even know what that is, Nb. Okay. It is no longer molybdenum. It is now Nb. How many protons does a gold atom? Here's an inset from gold. 79. Okay? By definition, never, ever, ever has a gold atom existed that didn't have 79 protons. An atom will not only have a periodic or atomic number. Do you have a question?
No, but I don't think your camera's working.
It is. I think after a while the screen goes off. If it keeps blinking, it's going.
Okay.
So not only do we have an atomic number, but we also have a mass number. And a mass number is the protons plus the neutrons. Remember, the protons and neutrons make up almost all of the mass of the atom. So if we have a mass number, that tells us combined protons plus neutrons. Okay. On a periodic table, it's basically this number. And we'll talk about why it's not exactly this number. Okay? But more or less, it is this smaller, this number down here is in a smaller font. Okay? The mass number equals protons plus neutrons. So if I tell you that I have a helium atom, so helium right here, helium atom that has a mass number of 3. How many neutrons does it have? 1. Why?
Because it has 2 protons.
Because it has 2 protons, and protons plus neutrons equals 3. So it means there's one neutron. Does that make sense to everybody? So we have helium. I said we have a mass number of 3. So 3 equals protons plus neutrons. Okay? And we got off of that, how many protons do we have? 2. So
Okay.
3 equals 2 plus n, so n has to be 1. Got it? Atoms of the same element, meaning they have the same number of protons, they have different mass numbers, means they have different numbers of, if it's the same element, it has the same number of protons. If the mass number changes, what's changing to cause that change in mass number? Number of neutrons. So atoms of the same element, they have different numbers of neutrons, we call isotopes. Okay? Anyone a Simpsons fan? Isotopes, right? A lot of elements have quite a few isotopes. Okay? Some elements only have one. Say, for example, if tungsten always had X number of neutrons, there would only be one isotope of tungsten. We use isotopes to our advantage. Okay? Generally, an element wants to have a certain number of neutrons. If it has more than that, it's going to emit radiation to get down to the number of neutrons that it wants. We're not going to talk about radiation, but anyone who works in medicine, you've probably used radiation, right? X-rays, things like that, okay? Or cancer treatment, radiation treatment, things like that. Those are isotopes that have more neutrons than they want, so they emit radiation. Okay. So hydrogen has 3 isotopes. Okay. Here is hydrogen. How many neutrons would you say that has?
1.
Yeah. If the blue has a +1 charge, that means blue is what? A proton. So how many neutrons does it have? None. So there's this isotope of hydrogen with no neutrons. There's an isotope that has 1, and an isotope that has 2. Okay. If you've ever heard of deuterium, deuterium is a hydrogen atom that has 1 neutron. If you've ever heard of tritium, tritium is hydrogen that has 2 neutrons. Okay. And at the bottom, you see these little symbols. Okay. This is sort of a variation of the atomic symbol. The bottom number here is the same between all of these. What do you think that bottom number means? Protons. What do you think the top number means? Protons and neutrons combined. It's the mass number. Okay? Because here we have no neutrons. We just have 1 proton, it's a 1. Here we have a proton and a neutron, it's 2. Proton, 2 neutrons, is 3. Okay? So when we write that, say we're going to deal with zinc. Write that. What number am I going to put here? Zinc is here. 30. It's the atomic number, it's the number of protons. Okay? So if I said this atom of zinc has 5 neutrons, what number do I write here? 35. It's the mass number. It's the protons plus the neutrons. So we call that an isotope symbol. And you can write this several different ways. They all give you the same information. There's this way that we just did it. So this is boron. How many neutrons does this atom of boron have? 6. So the mass number of that boron atom is 11. You can write that as boron 11. Okay? It doesn't, in numbers, tell you that there are 5 protons. But if you know the name is boron, You can look at boron up there, find the atomic number, and that tells you how many protons there are. If you know how many protons, you can figure out how many neutrons, right? And then you can also write it the same way, but instead of writing the element out in words, you give the symbol. All of these tell you the same exact thing. These two just require you to do a little bit extra work. So, here is an atom, and this is a blown up picture of the nucleus. How many protons and how many neutrons are in this nucleus?
5 protons.
5 protons, 1, 2, 3, 4, 5. How many neutrons?
6.
1, 2, 3, 4, 5, 6. Okay? What element is this? Boron. There's 5 protons, which means the atomic number is 5, and 5 is boron. What is the mass number? 11. This is our boron 11 atom. So I will give you a hint. Going between these mass numbers, number of protons, number of neutrons, and then as probably next we'll see number of electrons is a very, very, very common quiz exam type question. Okay? They can give you any sort of combination of things and make you find the missing one. Okay, so here is a different atom. Someone help me write 2 different isotope symbols for this atom. Yeah.
So you can better.
Go ahead. Sure. And why did you get that? Or how did you get that?
Well, there's 3 protons, so 3 up there is lithium.
Right?
And then there's 4 neutrons plus 3 protons is 7.
Right.
Just the mass number.
Exactly. So there's 3 protons, which means it's lithium. So you wrote lithium, and then you wrote that 3 there. 4 neutrons, 3 plus 4 is 7. You put it there. What's another way I could write that?
Li dash 7.
Lithium what?
7.
7. It's the mass number. Okay. How many protons are in this atom? 17. How many neutrons? 18. How did you get 18?
Subtract 17 from 35.
Right. 35 minus 17 is 18. How many protons are in that atom? 6. Carbon is 6, so there's 6 protons. How many neutrons? 5. So 6 plus 5 is 11. How many protons are in this atom? 79 protons. So, how many neutrons?
119.
You got 198 minus 79 is what?
119.
119, so it's 119 neutrons. This simple enough?
Didn't show.
Yeah, that's
side
shown
on my
on my
slide.
That? It's not there?
No, I think when it prints black and white, some of the stuff is
Yeah.
faded, so
Right.
I just have to.
I struggled with that last semester. I cannot find a way, even if I save it in black and white, it does that.
Well, I do it in color, and the yellow doesn't come up very well on the.
Yeah.
You can kind of see it.
Everybody got it? So, what is an isotope symbol for carbon-13? So what's the symbol for carbon?
C.
C.
6 at the bottom.
6 at the bottom, 13 at the top. So carbon-14 would be the same except we'd have 14 here instead of 13. That's the only difference. What about, what's the symbol for chlorine-37? Chlorine is there. So you have chlorine-17 with, if we're doing chlorine-35, it'd be 35. If we're doing 37, it'd be 37. Right? Did that one print out? Or is that one you have to copy too?
It's like faint. The answers are faint.
The website that makes you do it in PDF, or can you do it as a Word doc? PowerPoint.
I can do it as a PowerPoint. I'm not sure if it's going to help you there.
Well, if it's PowerPoint, you go through and highlight all the yellow and change to another color before you print it out.
I can try it. Unfortunately, a lot of these here,
Don't convert.
they're not actually, they don't, PowerPoint doesn't see it as text, it sees it as an image. So I may not be able to. Anyone want to do these other ones? Oh, they're the same thing. Okay. So now on to ions. Ions are where we start actually doing something. Things start changing. The sodium atoms that we eat, the sodium atoms that your doctor says to not eat as much of, are ions. Okay? Sodium in the ocean is in the form of an ion, not a straight up atom. A sodium atom has a net +1 charge. If a normal sodium atom has 0 charge, how do you think we got from 0 to +1? There's two potential ways you could do it. There's two ways you can change the charge of something, right? If you add a proton, what happens?
Positive.
It goes positive. But what happens when you add a proton? You change the element. So if you took a sodium and you added a proton, it's not sodium anymore, it's magnesium. So how can we take a sodium and give it a +1 charge? Yeah.
And a
Just
neutron.
give away an electron.
Take away an electron. If we added a neutron, what would happen? Nothing. Neutrons have 0 charge. So you can add them all you want, or subtract them all you want, and it doesn't affect the charge. But if you take away an electron, electrons have -1. So if you start at 0, and you take away a -1, 0 minus -1 is what? +1. So we went from 0 to +1. Before, there was 1 proton for every electron. They cancel each other out, and you had a net of 0. If you remove 1 electron, then there's 1 proton sitting around that doesn't have something to cancel it out. You now have +1. How many protons and electrons does a sodium ion have?
Sodium or sodium?
Sodium ion. First of all, how many protons does it have? 11. That doesn't change. It's sodium, so it's 11. How many electrons do you think it has? 10. Okay. So, if we lost 1 and we're at 10, how many did it have to start with? 11, which is the same as the atomic number, right? So when you talk about atoms, neutral atoms, not ions, the atomic number also tells us how many electrons it has. Okay? Is this the one that has a giant picture on it?
Yes.
Yeah.
Okay, I realized that after I submitted it. Okay, so you're gonna have to write around it. Okay. So, ions come from atoms when you change the number of electrons. You can either gain electrons or you can lose electrons. When that happens, you either have more or less electrons than protons. which gives you a charge. There are two types of ions. This is really, really important, okay? Two types of ions. The first is called a cation. A cation is any ion that has a positive charge. If it's an ion and it has a positive charge, it's a cation, which means that it lost electrons. The other one is called an anion. Anions are negatively charged, which means they gained electrons. Okay? You're going to come back to this over and over and over again this semester. If you have a cation, did it gain or lose electrons? It lost. If you have an anion, what charge does it have? Negative. You're just going to have to remember that. Okay? If you need to copy more, I can put this slide back up at break. Okay. So cations, positive. If that helps to remember, go for it. Last year I had a grumpy cat one that was very confusing because grumpy cat I said was negative, but then there's a cat and it's negative, and that just didn't work.
I just use the T as like a plus sign.
That works too. That works. Any way you can remember it, good for you. Okay. So this is a magnesium atom going to a magnesium ion. Remember, this arrow means going to, or yields. This yields that. Okay? Here we have 12 protons, 12 neutrons, 12 electrons. Completely neutral magnesium atom. Magnesium, when it forms an ion, loses 2 electrons. When that happens, it now has 10. And we write that as this Mg2+. Okay? This superscript here is the charge on that atom. Okay? It's a 2 and it's a positive. You don't want to write Mg +2. I know what you mean, but technically this is the correct way to do it. This is a nitrogen anion. Here we have 7 protons, 7 neutrons, 7 electrons. Nitrogen likes to gain 3 electrons. So here we have it, went from 7 electrons, 10 electrons. We have N with a 3 minus charge. How many protons does a sodium ion have? I think we already did this. How many protons does a sodium ion have? 11. How many electrons? 10. How many protons does a chlorine ion have? 17 protons. How many electrons? 18. It started with 17. It has a -1, which means there's an extra electron. So 17 plus 1 is 18. How many protons in an oxygen ion?
2 or 8, sorry.
8. How many electrons are in this ion? 10. 8 plus 2 is 10. How many protons in an aluminum ion? Aluminum is there, it's 13. How many electrons? 10. 13 minus 3 is 10. So now we're gonna go the other direction. Write symbols based on number of protons and electrons. So first one, we have 20 protons, 18 electrons. What's my symbol? 20 is calcium, so I write Ca. What's my charge?
+2, 2 plus.
Right. 2 plus. Because there are 2 more pluses than there are minuses, right? What about number 2?
2 minus.
I mean.
What's my symbol? What's my symbol?
Air.
6,
Sulfur.
I think it's
16 is sulfur. And my charge is 2 minus. How about number 3?
Iron.
Iron is Fe.
3
3 plus. Everyone okay going that direction? The mass number tells us relative masses. Okay? A carbon-12 atom weighs 12 times as much as a hydrogen-1 atom. Okay? But when we're dealing with atoms, the mass is so small that the unit is nothing we can comprehend. It's so small. This mass number is not an actual mass. All it is a number that we can use to compare one atom to another in terms of relative mass. Okay? The units we use are called atomic mass units, or AMUs. And this was developed using carbon-12. So they said, what is the mass of a carbon-12 atom, and then one atomic mass unit is 1/12 of that. We're going to say if carbon weighs 12, then carbon has a mass of 12 atomic mass units, which means something with a mass number of 1 weighs 1/12 as much. Okay? That probably seems confusing. That whole concept isn't all that important. What you need to know is that we talk about masses of atoms with the units atomic mass units. And you can use that to compare one atom to another. Okay? So if I have carbon-12 and I have carbon-13, the carbon-13 is 1 AMU larger, or heavier, or more massive, wherever you want to put it. Each proton and each neutron equals 1 AMU. Okay? If I say carbon-12 weighs 12 AMUs, it has 6 protons, and it has a mass of 12, that means it has 6 neutrons. 6 plus 6 is 12. So 1 proton equals 1 AMU. 1 neutron equals 1 AMU. We say an electron has negligible mass. We ignore that. Okay? The numbers up here are not whole numbers, right? So if we're saying the mass is the proton plus the neutrons, and I'm telling you now you can't split a proton or a neutron, how do you get a non-whole number? These are actually averages. Okay? We said that each element has different isotopes. If you have a whole bunch of a certain element, you have a mixture of all those isotopes. But all of those isotopes have different masses. So what this number tells you is the average mass of any given atom that you have. Okay? So if you're dealing with a large number of atoms, because atoms are so small, in our world, we're always dealing with a large number. You can take an average, okay, and it's going to work out. You don't have to worry about this one is 12, this one's 13. The average is 12.01, okay? So if I told you that there were only two isotopes of carbon. We already know that there's three, there's 12, 13, and 14. But if I tell you there's two, there's 12 and 13, and the average of them is 12.01, is there more of the 12s or more of the 13s? More of the 12s. Why? Because it's closer to 12. Does that make sense to everybody? If you have a mixture of something, say I have a beaker, okay, and let's say there are 3 carbon 12s, okay, and 2 carbon 14s. If I wanted to find the average mass of those, mathematically, how would I do it?
Add them up and divide.
Right, so I would have 12 plus 12 plus 12 plus 13 plus 13, right? So then I get a number and I divide by 5. Whichever number there are more of here, your average is going to be closer to. So if this 12.011 is very, very, very close to 12, and I'm telling you there's also a carbon 13, that 13 must not figure into your average very much. So there must be a whole lot more 12 than there are 13. So now if we go back to real life and I say there's carbon 12, 13, and 14, what does that tell you that it's very so close to 12? Right. There's almost no 13s, there's almost no 14s. Almost all of the carbon is 12. Here is silver. Okay. Silver, right there. Average atomic mass is 107.9. Here it says silver is composed of 107 and 109. Which one is there more of? 107. Because 107.9 is slightly closer to 107 than it is 109, right? So what does that tell you? Now we know if 107 there's more of it. Is there a little bit more of it or a lot more of it? A little bit more, right? So if we're going to calculate relative atomic mass, this looks really difficult because it's in a non-mathematical form, okay? When we do this, it's going to be really simple, okay? Here is an unknown element. We're calling it its symbol X, okay? We discovered it on another planet, and we know that it exists in 2 isotopes. In this table, we're given the atomic masses, percent abundances of both of them, and we're supposed to find the relative atomic mass of the element. The relative atomic mass is our average atomic mass. To do this, all we do is we take one isotope at a time. So we'll take the top row, the 22. Our mass is 21.995, and we multiply it by the percent abundance in decimal form, not percentage form. Okay? So what's the decimal form of 75%? 0.75. Times 0.75, we do the same thing for the other one. That's 19.996 times what? 0.25. We just add these together, okay? So what is 21.995 times 0.75?
How far do you want to round it?
Let's take it to 3 decimal places.
16.496.
496, and what is 19.996 times 0.25?
4.999.
4.999, and then add those 2 together.
21.50.
21.50. So, let's look at our sig fix. How many sig fix should our answer have?
Two,
Where you getting to?
cause 0.75.
So I actually kind of, because this is 75.00, so that's to that,
Okay, so 4.
4. So in our answer, that's how many?
4.
4. So we have our sig fix. What's missing here? Units. What are our units? AMUs. We're talking about atoms. AMU. Okay. You may see that sometimes capitalized, sometimes you may see it lowercase. It's the same thing. A periodic table is organized in the way we read things, top left to right, top to bottom, in increasing atomic number, right? So it's increasing atomic number. What is also increasing?
Mass.
So it was
Atomic mass?
mass. Mass goes up generally. As you go along, you may see one or two exceptions, but generally, as you go, the mass goes up. Why is the atomic number going up as you go down? What determines the atomic number? Protons. So, our periodic table is organized also in terms of increasing number of protons. It has a funky shape, right? It's not just a block of elements. And we'll see why that is. But if you ignore the gaps, go 1, 2, 2, 3, 4, 5, 6. This periodic table likes to show hydrogen in both places, there and there. In some cases, it helps to think of it as being there. In some cases, it helps to think of it there. It's both hydrogen. It's the same exact thing. They're just showing it in both places. Okay. So you have 1, 2, 3, 4, 5, 6, 7, and so on. Down here, it goes 56, 57, and then it goes 58, 71, and then comes back up here. Okay. That is really inset there, but if you inset that there, the periodic table would be really, really long. So they put it down here to make it shorter and more manageable. Columns we call groups. Okay. This is group 1, group 2, 3 through 18. Okay. Things that are in groups have very, very similar properties. Everything in group 1 is going to behave very similar to each other. Everything in group 2 is going to behave very similarly to each other. And we'll see why that is, but sneak peek, it's because they all have the same number of electrons. Okay? You almost always hear that called a group. You may also, in some cases, see it called a family. Okay? Group is by far the most common thing. I will never call it a family. A horizontal row is called a period. Okay? As you go from left to right, I say properties change in a periodic fashion. That's why it's the periodic table. If you go from left to right, as you go from left to right, you're going from one group to another, to another, to another. But if all the atoms in a group change the same, the change going from left to right here is going to be about the same as going to change from going from here to here. The properties are going to change the same way. Okay? We call these periodic trends. An example of similar properties in our groups is group 1. Okay? Group 1 reacts very, very violently with water. Okay? I think in was it the post lab that we were looking for a chemical property of sodium or potassium? I think it was sodium. And some of you that asked, I said a chemical property of sodium is that it reacts violently with water. Has anyone ever seen or heard of someone putting sodium in water? Yeah, it does that, and that's kind of tame, okay? Basically what happens is it gives off hydrogen gas and also gets very, very hot. And hydrogen gas is flammable. That's what was in the Hindenburg, right? So if you give off hydrogen gas and a lot of heat, you then ignite that gas and you get flame and sparks and all kinds of stuff, okay? When I was an undergraduate, I was working in a lab, and I was in a room, and there was people in the lab next to me, and they had sodium that they had to get rid of. And the EPA or OSHA or some safety, I don't know, makes it really difficult to get rid of sodium solids, because if it comes in contact with water, it blows up. So they said, well, if I put it in water a little bit at a time, I'll make sodium hydroxide, and the hydrogen will go in the fume hood and it won't do anything, and then I have sodium hydroxide I can get rid of really easily. So they started adding a little bit of sodium at a time, and if you have a bunch to get rid of, and you're adding a little bit, what happens? You get impatient, right? So they got to the last little bit and said, this will be fine, let's just throw it in there, okay? They put it in there, and it basically shook the walls, okay? There was this big metal press that was on a bench in there that was about this big around and about that tall. I don't know how much the thing weighed. It was so loud, it shook the walls, the whole floor. I felt the floor buckle, okay? I thought that big metal press had fallen off onto the floor. But it was a little tiny piece of sodium about that big that they put in the water, okay? Not condoning this, but if you go on YouTube, you can probably find some pretty interesting videos, okay? And actually, as you go down, the reaction becomes even more violent. So potassium is even worse. I don't know anyone who's ever put rubidium in water, okay? But everything in that first column reacts very violently with water. That group 1 we call alkali metals. Remember that name, okay? That's one of the learning objectives, is knowing the names of some of the common groups, okay? Group 1 is a very common group. Hydrogen, sodium, and potassium are everywhere, right? They're very common. Alkali metals are group 1. We talked about metals, nonmetals, and metallites, right? There's a stair step, starting boron and going down. That separates the metals from the nonmetals. What side are the metals on? Left. Majority of the elements are metals. On the line are the what? Metalloids, and to the right are the nonmetals. Okay. Metalloids look like a metal, okay? But they react and act more like a non-metal. Has anyone ever seen pure silicon? Not silicone is actually different than silicon, okay? Silicon is what's in microchips, okay? It looks like a metal, okay? Next time we're in lab, by the little office there's a periodic table that has pictures of all the elements. Take a look at it. It looks like a metal, but it does not behave like a metal. So here are metals, they're shiny, right? Here are metalloids. See, they're silicon. I would say that's shiny. Shiny, we said, is an example of a property of a metal. But the reason silicon is used in microchips is because when it's in its pure form, it does not conduct electricity, which is the other requirement to be a metal. Okay? In terms of reactions, it definitely does not behave as a metal. So, we can group our elements by several different ways now. We have our groups, the columns, we have our periods, our rows. This is period 1, period 2, 3, 4, going down, we have metals, nonmetals, and metalloids. And a fourth way, which is easy, is the main group elements. Main group elements are here. Okay? Here it is. All right. This isn't as easy as it should. Hold on. Main group. Transition metals. Okay. Cross out this term, inner transition metals. Cross it out, okay? I don't know what they're talking about by that, and I didn't catch that when I went through these slides. So you cross out inner transition metals, okay? So now you have main group elements and transition metals. Transition metals are this inset here, okay? Anything to the left, these, or anything to the right are main group elements. Is anyone confused about that? I made it more confusing than it had to be with the slide. So you have transition elements in the middle, main group elements on the sides. So we said group 1 is alkali metals. Those are alkali metals. Group 2 is the alkaline earth metals. Okay? You have to remember those two. Okay? The easiest way to do it is just remember somehow. Maybe here there's one word, so it's group 1. Here there's 2 words, so it's group 2. Okay? I remember it. For some reason, to me, calcium seems like an earth metal. I don't know. But I remember calcium, earth, so the group that has calcium in it is the earth, is the alkaline earth metals. It doesn't really make sense, but it helps me remember it. So if you can find something that helps you remember which one is the alkali metals, which one is the alkaline earth metals, that's all you need. Okay. On the other end, down here, we have the halogens. The halogens are this one. Group 17, the second to last one. Okay? You're going to use these a lot. Okay? They're nonmetals, and they exist as what we call diatomic molecules. You'll never see a fluorine atom floating around on its own. You'll never see this hydrogen atom floating around on its own. Chlorine, bromine, iodine, I think that's astatine. Okay. These are all really common. Down to iodine, you'll run across that all the time in the semester. Astatine, not so much. Okay. But they exist as diatomic. So if you want to write chlorine in its atomic form, you're actually going to put Cl2. There's 2 chlorines that come together. And we'll definitely come back to this. All the way on the right-hand side are the noble gases. Okay? They're called noble gases because they don't react. They say they're noble, they're too good, they're too elitist, they don't want to interact with anybody. They just do their own thing. Okay? In this class, we say they do nothing. In the real world, krypton and xenon can do a little bit. But to us, noble gases don't do anything. Okay. So, the halogens are not the only diatomic molecules. There's the halogens, and then nitrogen and oxygen. Okay. So you get this little L shape, plus hydrogen. Okay. You're going to have to know which ones are diatomic. Most of it will come just by practice. Anything in that little L is going to get used all the time. If you get it marked wrong 3 times, by the 4th time you're going to get it right. Okay? But you don't want to do that. Memorize it the first time. Nitrogen to fluorine and down, and then hydrogen. Okay? All of these will exist as these diatomic molecules. So if you find yourself writing by itself, N. No charge, no nothing, just N. Something is wrong. Okay. We said sodium loses an electron and becomes +1. Okay? Everything in this first column loses an electron, becomes +1. All of them, okay? No exceptions. Alkaline earth metals form a +2 charge. How many electrons do these lose? 2. Okay? Oxygen and sulfur form -2 charges. How many electrons did they gain? 2. Halogens form -1s. They gain 1 electron. Do you see a pattern?
Closest to the noble gas, like, for example, fluorine,
Mhm.
you need 1 to get to.
Right. So, noble gases are at the end, right? Things want to get to the noble gases. Okay. Chlorine, fluorine, the halogens, they're 1 electron short of having as many electrons as the noble gas next to it does. How many electrons does a neutral chlorine atom have? How many electrons does a neutral chlorine atom have? 17. How many does a neutral argon atom have? 18. So, if chlorine can gain 1, it will have the same number as a noble gas. So it does. Everything in this column likes to gain 1 so that it can more or less move over here. This column, oxygen and sulfur, are too short of a noble gas. They like to form a -2 charge. So they like to gain 2 to get to here. Okay? What do you think is going on with these losing 1? Why don't they gain 7?
Because the one is shorter than gas.
Right. It's a whole lot easier to lose 1 than to gain 7. So if sodium loses 1, it goes back 1 to neon, and it's like a noble gas. Okay? So these like to lose 1 to go back to here. These lose 2 to go back to here. These gain 1, gain 2, gain 3, gain 4. Okay? So you're going to do that over and over again this semester. Okay? You're going to be dealing with an ion of an element, and you're going to have to figure out what charge it forms. Okay? So if I ask you, what is the charge on a barium ion? Barium is right there. What is the charge on a barium ion? It's 2. Does it gain or lose? It's going to go backwards, right? So it's going to lose. If it loses negatives, then it is 2 plus, right? Actually, I didn't never pass this around. Noble gases are already where they want to be, so they don't have to go anywhere, okay? What is the charge on a phosphorus ion? Phosphorus is there. 3 minus. It's closer to the right side, so it's going to gain to go this way. So it's going to gain 1, 2, 3. Okay? Does that make sense? It wants to get to the closest noble gas. If you're on the left, you want to go that way. If you're on the right, you want to go to the right. These transition elements, in general, there are some exceptions that we'll see, in general, form +2. So you go +1, +2, and then these are all +2, these are +3, and then these can go this can go 1, 2, 3, 4, +4, or it can go 1, 2, 3, 4. The ones in the middle are kind
Is
of
it right either way?
It depends on the situation. It's very, very going to be very, very, very rare probably so rare it's never, that you're going to be dealing with this group in terms of ions. It just doesn't happen, okay? Because the more electrons you have to gain or lose, the harder it becomes. And there's sort of a threshold at that 4 where it just doesn't happen. The way this, anyone see what this, how does this help you remember anything?
Like rock.
It's not, it's rock, but what kind of what kind of rock?
Hard.
Metal. So it's like cations are metals. Okay. That didn't work.
Skip.
And will you go back to this one so we can copy it later as well?
It just reminds me. So, we say that noble gases have 8 valence electrons. Valence electrons is a very important term. Valence electrons are on the outside. Okay? We say noble gases have 8. If I say that neon has 8 valence electrons, we start at the left. There's 1, 2, 3, 4, 5, 6, 7, 8. Okay? When atoms lose or gain electrons, they're trying to get to 8 valence electrons. If you have 2 extra, say calcium has 2 extra ones floating around, and it loses those 2, we're going to see it goes down to the next electron shell. Okay? And that one is full, it has 8. So you go backwards to the argon. Okay? Everything wants to have 8 valence electrons. That's going to determine what ion it forms, and it's also going to determine what reaction it goes through. Okay. Metals, like we said, will lose electrons, become positive, form cations. Non-metals will gain electrons. They become anions, which are negative. How many electrons does a sodium ion have?
How many electrons?
Yes, how many electrons does a sodium ion? I don't know if I said ion or atom, but I mean ion. 10. Yes. Started with 11 and went backwards 1 to neon, which has 10. What about magnesium? How many does it have? 10. It lost 2 to go back to neon. What about aluminum? 10, right? Oxygen? What did it have? 10. Fluorine? 10. Right? Everything is sort of meeting at this 10. If you can gain or lose electrons to get to that noble gas configuration, that's what they're going to do. What is the charge on a beryllium ion? Beryllium's right here. 2 plus. What about aluminum?
3 plus.
Sorry?
3 plus.
3 plus. And phosphorus?
4 minus.
3 minus.
3 minus. Which is 1, 2, 3. Okay? It's just a matter of counting. Okay? Just find your element, figure out if it's easier to go to the left, or go to the back, or to the right, and then just count. Arsenic, you say 1, 2, 3. Minus 3. Radon, you can go 1, 2, which will bring you back to, actually that's not radon. Back to the radium. To bring you back to radon. may have seen an atom drawn like this before. Okay, we call this Bohr's model. Okay, it's a really easy way to think about atoms, and we can use it to some extent, but in reality, it's wrong. Okay, we draw this with a nucleus in the middle, and then these rings going around. And then we number the rings 1 through however many we need. Okay? And then as we go out, we add electrons. So if we add the first electron, it would go in the first one. Then as we add them, they would work their way out. Okay? But that is not how it works. There are not these really simple orbits, like a planet going around the sun. It's the cloud that we talked about. Okay? Basically, electrons are in an orbital. Okay? They are not round, they're weird shapes, and they, at any given time, they can be anywhere in that orbital. Okay? An orbital, we say, it's this three-dimensional shape. It's a space. And electrons can be anywhere in there. Okay? So this one happens to be spherical. Okay? The electron doesn't have to be on the outer edge of that. Okay? It's a three-dimensional sphere, and it can be anywhere in there. It can be in the center, it can be on the outside, it can be anywhere. Okay? It's just flying around. Then we have a term called principal energy levels. Principal energy level are orbitals of similar size. On the periodic table, it's the row number. Okay? So, elements in this row are filled to the third principal energy level. Okay? As you go from left to right, adding electrons, because this one has 1, 2, 3, 4, 5, 6, 7, 8, you're filling that principal energy level. There are 4 types of orbitals, S, P, D, and F. Don't worry about the shapes. Okay? They get really funky. You would never be able to draw that on an exam, so don't even worry about remembering what they look like. Okay? This is just showing you that they have different shapes, and then you can see F orbital kind of looks like it might be able to hold more electrons than a D, which looks like it may be able to hold more electrons than a P, which looks like it may hold more than an S. Right? But what you do need to remember is that they're called S, P, D, and F. And we were going to use this enough times that you don't have to make a specific point of remembering that. The shortcut, the periodic table will tell us where the electrons go. Okay? These 2 groups are S. These transition metals are D. These are P's, and these are F's. Okay? So as we add electrons going from the top left to the bottom right, we fill orbitals as we go. We'll do plenty of these. Just remember, you have S's, D's, P's, and F's.
But helium and hydrogen are still S, right? Since they're found on both sides?
Yes. Very, very good. We'll see that. The first period is an exception. There are only 2 there. In this case, you see how they wrote helium? Somebody actually wrote helium there. In this case, it helps to think of helium as being there. Okay, and we'll see the S and why that, what's going on. We write electrons in these orbitals several different ways, and we're going to do all of them. Okay. The first one is called an orbital diagram, and I will point out there's going to be orbital diagrams and electron configurations. They tell you the same thing in a different form. You're going to have to remember that an orbital diagram is the one with the boxes and the arrows. Okay? Some homework problems, some quiz problems, some exam problems will ask you for orbital diagram. Some will ask you for electron configuration. You have to know which one is which. Okay? The first one we're doing is an orbital diagram. It's the one with the arrows and the boxes. So, we're dealing with carbon here. Carbon is there. Okay? When we start filling these orbitals, we start in the orbital in the top left corner and work left to right, top to bottom, filling as we go until we get to the element that we're stopping at. Okay? How many electrons does a neutral carbon atom have? 6. So we have to place 6 electrons. Okay? So we're going to start in the top left corner. Top left corner, we say it's a 1 because it's the row 1, it's period 1. So I'm going to write 1, and hydrogen and helium, do you see how normally this S has 2? Okay? See, if this is S, the 2S contains 1, 2. The 5S contains 1, 2. Okay? Helium is this weird example. It's the second one in 1S, but it's way over here. Okay? So we write our 1S. S's get 1 box. Write that down. S's get 1 box. Each box can have 2 arrows. An arrow represents an electron. So our 1S is going to have this electron and that electron. And you notice how the arrows in 1S, there's 1 up, 1 down, right? If you have 2 arrows in a box, they cannot point the same direction. Okay? What this represents is the spin of an electron. Electrons, not only do they fly around, but they also spin like a planet. Okay? And based on really complex physics, 2 elements in the same box or orbital cannot spin in the same direction. Okay? If you've ever heard of Pauli exclusion principle, where you can't know how something is moving, how fast something is moving, and where it is at the same time, it's related to that. Okay? So if you have 2 arrows, one of them has to be up, one of them has to be down. Okay. So we filled 1S. So now we're in row 2. This is 2S, right there. So that's the next thing we're going to fill. So we're going to fill 2S. It's an S, so how many boxes does it get? 1. Carbon is here. It's past this 2S. Does everyone see how it's past 2S? So I know that this box is full. Okay? What orbital is this here? P. P's get 3 boxes. Write it down. P's get 3 boxes. Even if you're not going to fill them all, you have to show 3 boxes. Okay. So it's a P, and it's still in period 2. So I'm going to write 2P and give it 3 boxes. How many electrons do you think carbon has in the 2p orbital? 2. We're going left to right, so there is 1, 2. Okay. S's hold 2 electrons, P's hold 6. 1, 2, 3, 4, 5, 6. So you can just count here. There are 1, 2 in the P. Okay. Now, we have 2 arrows have to go in this box. Okay? Up there you see they put 1 here and 1 here. They did that because you don't put electrons in a box with another electron if there's an open box for them to go into. Okay? So, if I was going to do the electron or the orbital diagram for nitrogen, what would it look like? I would add an arrow here. If I was doing oxygen, what do you think I would do?
The first box was first
I would add a down arrow here. What about fluorine? Add a down arrow here, and then neon would be full. Okay? Now, that's one way to do it. You can start and say, okay, I did 1S, I know they're full, let's fill it. I did 2S, I know they're full, let's fill it. Let's go to 2P, draw the boxes, figure out how many I have. Okay? The other way to do it, actually, let's erase. Is to say, what orbital is the last electron in carbon in? It's in 2p. So the carbon is located in 2p. So I'm going to draw all of the orbitals up until 2p. Now, how many electrons does carbon have? 6. So now I've already drawn them. I go back and fill them all in at once. So I fill as I go. So I fill my S, I fill my 2S, and then I go like that, and that's all the electrons I have. So I stop.
Would it be wrong if your arrows were the 2P were facing down to start with?
They would be, if you did that the whole way through, where the first one is always down, it would not be incorrect. It would be incorrect if here the first one was up and here they were down. But the convention is to do the first one up, second one down. So here's our rules again. S's get 1 box, P's get 3. We didn't do a D yet. D's get 5 boxes. Okay? If there are 5 boxes, 2 arrows or electrons per box, how many electrons are in a d orbital? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Counting game. Well, that's all you got to do is count. Okay? Each box gets 2 electrons or arrows. Orbital numbers are the principal energy levels are the period number. The exception, and I guarantee you, some people are going to get it wrong because it doesn't make sense to begin with. The D's, here, the number is shifted back 1. This here looks like it's in period 4. It's actually 3D. That is in 5. It is 4D. Okay? Where that comes from is the order of orbitals electrons want to go into. Electrons want to do what is easiest. Okay? And if you imagine this 3D shifted up 1 here, okay? If you were at magnesium and you wanted to add 1 more electron, if this were shifted up, you would go from there to scandium, and that would be here, okay? But through experimentation, we know that electrons prefer to go into 3p before they go into 3d. So this is the order that they actually get filled in real life, which is why if you go top left, the bottom right, that's the order that they actually get filled. So you will put electrons into 4s before 3 is actually full. Okay? If you don't remember any of that theory, don't worry about it. Okay? Just remember, the numbers for the D's are shifted back 1. Okay? So, say for titanium, you're going to go 3s, 3p, 4s, 3d. Okay? The F's are actually shifted back 2, but we are never going to deal with F's in this class. Okay? Hold me to that. If some homework or something has an F in it, hold me to it. Okay?
Write that down.
Write it down.
It's recorded. We're good.
Yes. By tomorrow, it will be
Edited.
it'll be in the eternity of the internet, right? Can't take it back. Okay. So these are those rules in word form. The Aufbau principle tells you start at the left and work right. That's all that means. Okay? Start at the left, start at the top left on the periodic table, work your way to the bottom right. Pauli exclusion principle means you can only have 2 arrows or electrons per box, and they have to be in different directions. And Hund's rule tells you, it's basically this. Don't fill this box until everyone has at least 1 arrow. Okay? Don't worry about those names. You're going to do enough of these that you're going to learn to do that just by doing it. Okay? But these are the names of the rules and why you do that. Okay. So what is the orbital diagram for hydrogen? What is the orbital of hydrogen?
S,
It's an S. Okay, what number? 1. So it's 1s. So here's my 1s. It's an S that has 1 box. How many electrons does hydrogen have? 1. So what do I write in this box? 1 up arrow. And I put an H there. That is the orbital diagram of hydrogen. 100% on the quiz. Okay? Just like that. What is the orbital diagram of phosphorus? Where is the last electron of phosphorus? 3p. So phosphorus is here. The last electron is in 3, and these are p's. So it's 3p. So I need to draw all of my orbitals up until 3p. Okay? So here we have 1s. What's next?
2s.
Right. 2s. How many boxes? 1. What's next?
3 BP. D.
Like 2 feet.
2p. So there's 1s. There's 2s. Then we come over here. That's 2p. Okay? Does everyone see that? So the first orbital was 1s. That's hydrogen and helium. There. The next one is 2s, which is this, and then we skip this gap here and come over here. This is still 2, but these are p's. So the next one after 2s is 2p. How many boxes does that mean? P's get 3, because there are 6 electrons in the p's, which takes 3 boxes. So I give 3 boxes. Where am I going? I'm going to phosphorus. Then what's next? 3s. How many boxes does that give?
1.
And then what's next? 3p. And how many boxes?
3.
1, 2, 3. Okay. How many electrons does phosphorus have? 15. Okay? So there is the quick way to do this and the long way. We'll start with the long way. Start at the left, fill in until you got 15. Okay? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? 15. That is done. Okay? That's the sort of really thinking about what you're doing way. The other way to do it is to say, what is the last orbital? 3p. How many are in 3p for phosphorus? For phosphorus? 3. So, if I notice 3 going here, that's going to go like that, right? Everything here, by definition, by default, is full. I can just do this. And I know that it's going to come out correct. Depends on how confident you are. Yeah.
Do we not get breaks in?
5 minutes,
Oh,
or
okay.
whenever we finish orbital diagram, it should be, this may be the last slide.
Oh,
Actually, that's it, because now we're going to electron configuration.
Wait, are
So-
we gonna do cobalt, which that one
Oh,
is
oh,
in
sorry.
the D?
Cobalt, yeah, very good. Cobalt. So, let's actually, we can actually leave this up here for now, okay? So, if I have 3P, what's after 3P? 4S. How many boxes? 1. S's get 1. Okay. What's after 4S? 3D. We're going from here to here, which is a D, and the D's are set back 1 number. Okay. How many boxes do D's get?
5.
5. I'm out of room, so I'm going to put the D's down here, but imagine them being here, okay? If you have room, they should be one big long line. So I'm going to put 3D, I'm going to make that many boxes. How many electrons are in the 3D for cobalt? Cobalt is here. 1, 2, 3, 4, 5, 6, 7. So let's put 7 of them into 3D. How do I do that?
Put an up arrow on all of them.
Right, so there's 1, 2, 3, 4, 5, 6, 7. So now my D's are done. I can come back and fill in everything before it. And then that, make sure